Hi, so this is an update on our crystal growth for alum video number 2. So as you can see for our crystal, as of now, I do not currently have any crystal growth in my vial, but it can be observed that a significant volume of the water has evaporated from the vial. And therefore, in comparison to the last alum video, there has not been a significant change in crystal growth. There are several environmental factors that may be affecting the growth of my crystal. One of them may be that I store my crystal vial on the windowsill. Although this usually means that the crystal would be placed in a cold environment, my windowsill is directly above my heater. So therefore, as a result, my crystal is stored in a relatively warm environment. And as we previously studied, as the temperature of the solution increases, the solubility of a solid also increases. Therefore, because of the warm environment that the crystal is in, the crystal may be experiencing a greater solubility than my peers, and therefore has a greater difficulty precipitating out of the solution in a crystal. Another environmental factor that could be affecting the growth of my crystal may be the humidity of the room that is stored in. My room is relatively humid, and humidity is a factor in how much water can evaporate out of a solution. So because my room is humid, the air does not want to draw so much water out of the vial, and therefore decreases the ability of the alum to crystallize. So talking about our alum, we can calculate the theoretical yield of our product by using the reaction equations that we solved in the pre-lab. So at the beginning, we started with a mass of aluminum of 1.01 grams, as you can see here. And by using the molar mass, we can convert grams of aluminum to moles of aluminum. And as we see here, that equals 0.037 moles of aluminum. So using the first reaction that occurs in the experiment, where aluminum solid mixes with OH minus plus 3H2O yields AlOH4 minus plus 3/2 H2, we can use this reaction and molar ratios to calculate how many moles of AlOH4 minus are produced. And because the ratio is 1-to-1 between Al and AlOH4 minus, we end up with 0.037 moles of AlOH4 minus as well. So moving into the second equation, we have AlOH4 minus plus H2SO4 yields AlOH3 plus H2O plus HSO4 minus. And using the molar ratios once again between AlOH3 and AlOH4 minus, we can solve that there will be 0.037 moles of AlOH3. Now moving into the third equation, which has AlOH3 in the reactant, we can see that the third equation does 2AlOH3 plus H2SO4 yields Al2SO43 plus 6H2O. So by using the molar ratios here, we can see that you have 1 mole of Al2SO43 for every 2 moles of AlOH3. And you have 2 moles of Al3 plus for every 1 mole of Al2SO43. So that'll yield 0.037 moles of Al3 plus. And now we have Al3 plus, so we can move into our final reaction, which is K plus Al3 plus 2SO4 minus plus 12H2O yields KAlSO42 times 12H2O. And by using the molar ratios again between aluminum 3 plus and the alum, and the molar mass of our alum, we are able to calculate our theoretical yield of alum, which is 17.76 grams. So now that we know our theoretical yield of alum, we can calculate our percent yield of alum using the percent yield equation. So recorded in lab, our actual yield of alum was 13.1 grams. So the percent yield equation is actual yield over theoretical yield times 100. So we did 13.1 grams of alum, our actual yield, divided by 17.76 grams, our theoretical yield, and multiplied it by 100 to get 73.76% as our percent yield. So my percent yield was not 100%, and several factors may be contributing to this. One factor may be that when we transferred the precipitated alum from the filter paper to the mass balance, some of the alum was stuck to the filter paper, and as a result, it was lost. Because the alum was lost, this would lead to a lower recorded mass of alum, and as a result, this would decrease our percent yield. Another source of error was that while waiting for the alum to precipitate in the ice bath, not all of the alum may have precipitated out of the solution. As a result, the recorded mass of alum would again be too low, and therefore decrease our percent yield.